Good day to each and everyone, especially to our dear panelists and our professor, Mr. Marvin Abu. We express our sincerest gratitude for attending our journal study. I'm Andre Harold Vicelino, and I would like to greet you all a pleasant day. We'll be presenting our journal article study entitled A Lagrangian-Lorentzian Procedure for the Coupled Solution of the Navier-Stokes and Shallow Water Equations for Landslide-Generated Waves. Together with my group mates, Mr. Jansen Arquines and Mr. Tristan Anthony de Regla. May I now call on Mr. Arquines for the introduction.
Thank you, Andre Celino, for the overview of the presentation for Lagrangian-Eulerian procedure for the coupled solution of the Navier-Stokes and shallow water equations for landslide-generated waves. We will start discussing the introduction, methods, results, and the discussion. Okay, let's proceed for the next slide, which is the introduction. A landslide-generated wave, or LGW, also called a landslide-induced tsunami, is a major natural hazard that occurs when a landslide impacts a water reservoir and that results in a large amplitude waves. One of the most affected by landslide-generated waves, or LGW, was the Fjord district of Western Norway. From its historical records, where it experienced at least two major LGW events every century, which results in numerous death cases. Furthermore, the effects of global warming increase the intensity and devastating impact of natural hazards, which as the landslide-generated wave. To reduce the devastating natural hazard, accurate modeling and prediction of LGWs are key of importance. Both experimental and numerical studies contribute to the forecasting capabilities used to comprehensively identify these natural hazards. Physical models and numerical methods are effectively helping to identify the key parameters of both the sliding debris and water reservoir, and also helpful in predicting the wave movements and characteristics. Numerical methods can be classified into three groups. One is wave propagation solver. Two, landslide and water motion equation are solved in a unique coupled model. And lastly, it is split into two, which is a near-field solver and a far-field solver. Near-field solver, Lagrangian Navier-Stokes model, used to solve the motion both for water and landslide materials. Also computes the landslide runout, impact against the water body, and wave formation. The image below indicates the equation and its variable with their meanings, where B is the velocity field, sigma is the Cauchy stress tensor, B is the body force per unit of volume, P is the pressure, rho and kappa are the material density and bulk modulus, respectively. T is the time, omega t is the updated computational domain, and T, or the uppercase T, is the total time duration. Far-field solver predicts the far-field wave propagation and a simplified form of the Navier-Stokes equation. The main assumption includes incompressibility, hydrostatic pressure distribution, and small vertical velocity. After integrating the equation from the seabed to the free surface, n or eta, a new set of unknown is obtained. The pressure P is replaced by the free surface elevation, or the eta, and the velocity U is substituted by the mean horizontal velocity U. And the equations are an extension of the SW equation, or shallow water equation, which include the modeling of the frequency dispersion for long waves. Okay, let's proceed to the method which will be led by Andre Celino.
Thank you, Mr. Arquines. Now, for the methods of the study, Figure 1 shows the full view of the near-field solver and the far-field solver for the study of the coupled solution of the landslide-generated waves. Based on the figure that is shown above, as landslide occurs and made its first contact with water, given its mean velocity and velocity in its specific depth, it generated a big wave that dissipates as it reaches the shallow water boundary. Moreover, the generated wave was completely absorbed by the PFM boundary. Figure 2 shows the solitary wave. This wave experiment is conducted using a piston type meter. The flow of water is rightwards, and it travels a distance of 180 meters until it reaches a slope. Figure 3 compares the solitary wave propagation obtained with the PFM to the experimental findings, the Boussinesq solution, and the analytical and mathematical solutions. It also shows the time evolution. Figure 4 shows the amplitude of the wave measured with the distance and time. This figure interprets the saving of the computational time that is based on the reduction of the duration of the PFM simulation to the intended time. Figure 5 shows the graph of the time evolution of the amplitude of the wave at the first stage. As also projected in the graph, it shows the dot lines which is the representation of the old data. As observed, the four data solutions have an identical behavior in the first part of the graph. Figure 6 and 7 shows the water landslide and the velocity of the water on top upon its impact with the stable water. As shown in the figure 6, the water landslide alone doesn't have a relevance effect with the test of the landslide generated waves. However, water landslide and impact has shown significant results to the representative of a realistic LGW scenario. Figure 8 shows the global view of the simulation of the landslide generated waves and the results of the near-field solver and far-field solver, as what is shown in the figure. As landslide occurred and made its initial impact with the body of water, it generated and propagated a wave. In addition, it reduced wavelength, wave height, and amplitude as the landslide made its first contact with the water. Now, we will now proceed to the results of the study. The researchers have come up with the results of their study based on the experiments that they made. In addition, the figures also projects the data of their experiment. The researchers adopt a one-way coupling scheme, which means that the NFS solution is insensitive to the FS1 in order to significantly increase the computation performance of the method and consequently to enable the simulation of the large-scale problems. Another benefit in terms of accuracy and efficiency is that this partition method allows us to really decouple the time and space discretization of the two solvers. Furthermore, the researchers had found out that the presented examples that comes from the various articles from the review of related literatures or reference, including 2D and 3D problems, had shown good results with the newly obtained partition method. The researchers also found out that the shallow water interface should be placed as closely as possible to the impact zone. Its results gives a major advantage of reducing the near-field solver domain. With regards to the FFS, the near-field solver can also be placed very close to the impact zone as long as the momentum of the NFS is well transferred to the FFS. The researchers deduced that the FFS incorrect amplitudes were due to the sliding material, same density, and the water present in the place. However, the far-field wave propagation and the momentum produces accurately. Lastly, the researchers concluded that if the main point of the study is to reproduce the main wave propagation that comes from the simulation of the landslide generated waves, the PFM analysis can be stopped immediately after it is done modeling the impact and the first wave formation of the water. The study allows the researchers to compute for an efficient NFS, FFS, LGW simulations. The researchers also reasoned out that an estimation of 90% time savings can help compare a fully resolved simulation of the LGW scenario. The researchers also came up with another solution that a reverse one-way algorithm is needed to simulate with high accuracy the impact of the tsunami waves produced by landslides.
No. Now let's discuss about the discussion of this research. So this research describes a partition method for predicting landslide generated waves episodes. However, there is a numerical situation or simulation of an LGW is a complex undertaking this research. Indeed, the computational techniques must be able to describe the landslide materials, complex constitutes behavior to deal with the fluid solver since this research tackles about the fluid that can impact on the water of the body, and these resulting to wave generations. Furthermore, LGW analysis includes distinct time and spatial scales for the close of landslide water impact zone, and far fields wave propagation. Finally, a large-scale three-dimensional or 3D geometric must be solved over a long time or a long period of time, making the computation of LGW analysis one of the most crucial part of this research. Since we are talking about the Lagrangian-Navier-Stokes multi-fluid solver, these are combined with Eulerian technique, a different technique based on bosonic shallow water equation and suggested strategy. Now, these are the finite element or the method used by Lagrangian solver to represent the landslide run out its impact on the water in the water body and resulting waves generation. Lastly, this research requires numerical approach, on the other hand, offer the capacity to anticipate both near and far field wave characteristics. Thank you, and that's all for our presentation. We are Group 6, and these are the Lagrangian Navier Stokes research.